Today we're going to practice graphing quadratic functions in Vertex form a little bit more, and we're also going to write some equations from a table. So let's recall what we did the other day, and this is our parent function or our mother function, and the table of that looked like this. And our graph looked like this. And this graph has a vertex at 0, 0. The shape is called a parabola. And this graph opens up. Now, something new today is we have something called the axis of symmetry. And your axis of symmetry is a vertical line where you could fold your graph onto itself. So our axis of symmetry here would be this dotted line, because I could fold my graph over that line and the parabola would land on top of itself. Well, you might realize that that is the x-coordinate of our vertex. So x equals 0 in this case, because our vertex is at 0, 0. So this is the vertical line that goes through the vertex and divides it in half. This domain is always -infinity, infinity, and the range, since we are opened upwards, 0, infinity, and this has a minimum value. A minimum at y equals 0. So that's just kind of a recap of what we wrote down the other day. And there are other forms of quadratic functions. We're talking about the vertex form here, but there is one called intercept form, and there is one called standard form, and we'll talk more about those later. But I included that here just so that you would know that there are other ways to write quadratics. We're not going to write them down here. And to recall again how we have the general form with our a, h, and k. When we have an a, h, and k, we have the vertex at h, k. Our axis of symmetry is at x equals h. And we have a min or max value of y equals k. So we were using both parts of the vertex with our axis of symmetry and our minimum max value. Remember, there is a reflection if a is negative. There's a vertical stretch if the absolute value of a is bigger than 1, and a shrink if the absolute value of a is less than 1. Then there's a translation, left or right, h units, and up or down, k units. Now, you may be saying that we just talked about this, we did this the other day. This idea of a, h, and k come up all the time, so we're going to spend a lot of our time now really getting that down and understood, so that way when we talk about it later, we're not spending so much time on what a, h, and k do. Let's look at this example down here. And the first thing I'd like to do is make my table, an XY table. And I'm going to put the vertex in the middle. The vertex here is 1, 4. And then going up by 1, so 2, 3. And then down by 1, 0, and -1. Your domain, again, is always -infinity, infinity. Your axis of symmetry, that's going to be at x equals 1, the x coordinate of your vertex. Min or max value, we're going to wait until it's graphed. I mean, you could look at it now, and if you can tell that we have a max, that's fine. But I always like to see my graph before I do things like end behavior, range, min, and max, just so I have it all done before that. In comparison, we can do the comparison now too. There is a reflection over the x-axis. There is a vertical stretch. Whoops, it should be an S. T. We do have a translation, right 1 and up 4. All right. Now we need to plug in our values here. If you plug in 0, 0 minus 1 is, 0 minus 1 is -1. -1 squared is +1 times -2 is -2 plus 4 is 2. We plug in -1, we get -4. And then these y values should be the same as well. And I'm just going to double check with my calculator. -2, parentheses, -1, minus 1 squared plus 4. We get -4. Okay, so let's graph this. Okay. Now that we have this graphed, we can clearly see that the end behavior, both ends are going down. So as x approaches -infinity, y approaches -infinity. And as x approaches infinity, y approaches -infinity. Your range, well, since both ends are going down, the smallest y value is -infinity, and the y coordinate of my vertex is the largest y value. That also means we have a max at y equals 4. So you see how all these match the y coordinate of the vertex, your min or max value, and the range, and then also your axis symmetry and your vertex match. On the next page, we're going to graph this one. So x, y. 1, 2, 3, 4. Our vertex in this problem is -2, -3. And our comparison are, we have no reflection. Shrink or stretch, we have a vertical shrink. Translation, we are left 2 and down 3. All right, now, oops, over here, our x values are going up and down by 1. If we plug in -1, see 1/2, parentheses, -1 plus 2 squared minus 3, we get -2.5. Now if we plug in 0, we get -1. So -2.5, -1. Now if you made those as fractions, that's okay. It's just I find that when I'm plotting points, decimals are easier for me to deal with. Yeah, 1/2 and 0.5, most people know that, like 7/3. It'd be much easier to have that as a decimal to plot than leaving it as 7/3. All right, let's plot these points. Okay. So then my graph will look something like this. Domain, -infinity, infinity. And behavior, both ends are going up. So as x approaches -infinity, y approaches +infinity. And as x approaches +infinity, y is also approaching +infinity. Axis of symmetry, that is x equals the x coordinate of my vertex. Your range is going to be -3, infinity, because our graph is opening up. And then our min or max, we have a minimum this time at y equals -3. And again, just you want to double check that your range, vertex, y coordinate of the vertex, and your min or max all have the same number there. Now down here, I want you to pause the video, and I want you to do this problem here, this graph, and then I want you to try these two problems, which is asking you for a lot of the same information, but without graphing. So let's see how you do on that. Pause it for a moment, and once you're done, unpause it to check the answers. Okay, let's look at the answers here. So here's the graph with the table drawn out and the domain range and behavior, vertex, axis symmetry, or AOS. This one had a minimum value, and then your comparison. So check these over real quick to see if we got the same thing. And then down here, you see that we are able to find out this information without graphing. If you need to draw just a rough sketch, maybe not a table, just to say, okay, this one is opened upwards, and the vertex will be over here somewhere, and it's going to go up. See, that's just a rough sketch, so you can determine your domain range and end behavior maybe a little bit quicker, but eventually you'll get to the point, if you're not there already, that you can look at these equations and determine all this information.